Hello everybody. It's been a really long time since I made one of these videos, but a couple of days ago I finished the schematics. This is my assistant. Her name is Ruby. Excuse me. A couple of days ago I finished these schematics, which kind of outline the relays and how they connect to each other to form a 1-bit ALU. And my 1-bit ALU, a long time ago, you'll remember the original design. I know I posted this somewhere. But this is it. As you can see, here's your two main inputs, A and B. And this ALU can do the following functions. It can do an OR function. It can do an XOR function. It can do an AND function. And the most important one of all is if you engage both switch 1 and switch 0, it'll give you a full adder. It'll add A and B together, binary. Also using a carry in. So, you know, A and B and carry in will give you an output and a carry out, depending on, you know, the situation. So yeah, so here's the 1-bit ALU. Oh, also I've added in this this B invert, which can be used to do subtraction, because this will immediately give you like a 2's complement situation. But we don't have to really talk about that. Anyway, so between the schematics, implementing this beautiful functional diagram, we have created this masterpiece. This is the adder implemented with 34 relays, and I'm going to demonstrate to you that it does work. Surprisingly, this is phase 1. Phase 2 is going to be simplifying this a little bit. I think I can remove 8 of the relays that are implementing the ORs, because, well, I'll explain that part maybe in another video. And I also think that I can like move some things around to minimize all these big long runs between all these wires. Anyway, so here's our power supply. We're sending 5 volts into the system. And over here is this is the output. Well, this is a multifunction display. It's going to be giving us the input and the output. If you'll notice, the one with the dot on the left, that's the carry out, and the one with the dot on the right, that is your output. And on the top, it's going to basically be the A input, B input, carry in, and then it's going to be, oh no, it's going to be A input, B input, carry in, B invert, switch 0, switch 1, and then it'll be our outputs. Here is a switch. This indicates, this is how we're going to do our inputs here. The first switch would be the A, the second switch is the B, and the third switch is the carry in. And this switch is going to basically be doing the functions. Switch 0, switch 1, and B invert. You can always refer back here. Here's B invert here. Switch 0, switch 1, carry in, AB. Okay, so the first function that we have implemented here is the OR. And you'll notice that the inputs A and B will go into the OR, and they'll go into this. This is a multiplexer up here, this implementation that I boxed in here. So basically lets me select which one of these I want to do. So I'm going to do the OR. So as you can see, that is switch 0 set to low or 0, and switch 1 set to high. And that'll activate this AND. And this OR will sum it all together. So, okay. So switch 0, 0, switch 1, 1. So this is switch 0 is already on 0. And I will now carefully switch, hold on. There we go. I've now switched switch 1 on, and you'll see like my little indicator is telling me that switch 1 is now activated. So this is going to do an OR. So basically that means if I just click down A, you'll see on the output there, you've got a high signal, which is appropriate. And then you'll see when we click B, you'll see we also have an output. A and B are the first two lights. The light here is indicating that switch 1 is on. And you'll notice the carry in light is on. That's kind of like a byproduct of the function. I might suppress that. I'm not really sure yet. But in either case, since it's an OR, the output is high. And then I'll turn off A. Okay, so now it's just B is lit up, and you'll see we still have the output. Then we've just implemented an OR. Yay! Okay, so now the next one here, you'll see is the XOR, and that's if I turn both of my select switches on, which I will now do. You'll see both select switches are on, and now we've got the B is turned on, and you see we have an output. But notice that when I turn on the A, in true logical functionality, you will see there we go, that the output is now off. So we had B turned it on, A and B turns it off, and of course now just A should turn it on again. Let me turn this guy off. This is just A is lit up, and you'll notice, ta-da, XOR has worked properly. The next function is the AND, which is right here. And that's switch 0 turned on and switch 1 turned off. So switch 0 turned on, switch 1 turned off. Oopsie. I gotta get switches that are human usable. Okay, so now we have an AND functionality going on. You'll notice here that we only have the A, and nothing is on. And now if I turn on the B, you'll see nothing is on, but yet when we turn them both on, ta-da, there's your output. It's kind of cool when you hear the little clicks, because those are the relays. Those aren't the switches. Those are actually these mechanical relays going on and off. Okay, so now for the most important part of the ALU, the actual addition circuitry, which involves this XOR, this AND, this XOR, and this OR. This is essentially right here your circuit for a full adder, 1-bit full adder. So let's activate the adder. How do we do that? We turn both of these guys off. So that's there we go. Now you notice that I had A and B turned on. So when we add in 1 and 1, what do we get? We get 2, right? So since this is only a 1-bit, what that's going to give us is it's going to give us 0 on the output, and it's going to give us our carry out. Now this light really matters right now, this little carry out light right here. You'll notice carry out is turned on, which is exactly how it's supposed to be. Now you notice if I have any one of these guys turned on, you're going to get your output is going to be high and carry out's going to be off. Let me turn on A again, turn off B. There you go, same thing. Now, of course, to be a fully functional full adder, we have to implement carry in, which I will now turn on. So now we've got, in this case, A plus carry in is going to give us carry out. And then, of course, A plus B plus carry in is going to give us carry out and an output. I could also invert B, which would give us the 2's complement of this gig, which you see is just carry out, because now B is negative, or 0. I'm not really sure why this light is a little dim here, this A light. I don't know if that's something weird going on or not. But notice, like, this is using a lot of the relays to get this output right now, and that's why our current is actually kind of high. You'll notice that as we activate less and less relays, the current will change. this is, I think, almost none of the relays being activated. Anyway, sorry, that's 10 minutes. That's a 10-minute video, which is actually very long, but I just wanted to prove that I have implemented at least iteration number 1 of my ALU. Thank you very much for watching.